Hello everyone, I hope you're fine and safe. Today I'm going to talk about the motor fault analysis. It is one of the videos in the fault analysis series. And let's see, my name is Salah Ataya. I'm a condition monitoring and reliability specialist. I have a bachelor's degree in mechanical engineering and I work in this field since about 12 years now, and I'm certified Cat 4 vibration analyst. Uh, before we start talking about the motor fault analysis, we will have a very simple and quick explanation of how the electrical motor working. Like, the motor is designed as, like, when current is passing through the winding or the coils, the magnetic field is created on these coils, and also by small electrical arrangement, which we don't need to know exactly all the details. This magnetic field can be a rotating magnetic field, and we can have like, for example, two pole three-phase motor. And if we can put like a rotor, like this rotor is be considered like a magnet inside this stator, you will see that the inside or the north side from the stator will run over the south side from the rotor, and the east or south side from the stator will running after the in or the north side from the rotor. That's why the motor will start to spin. And if it rotates at the line frequency, which is 50 or 60 hertz, we call it synchronous motor. The other type, which is the three-phase induction motor, rotating magnetic field induced current on the rotor. That's why we call it induction, because it's induced this current on the rotor, causing the rotor to spin. And the line frequency could be 50 or 60 hertz with two pulsations per cycle. And this is what causing the twice line frequency to appear on the spectrum. And the phase difference between each electrical cycle is 120 degrees. There is some equations, basic equations you have to know before doing the analysis to the motor. The first one, which is the synchronous speed, it's equal to twice line frequency over the number of poles. And the slip frequency, which is equal the synchronous speed minus the rated speed. And you have pole pass frequency, which is equal the slip frequency multiplied by, slip frequency, yes, multiplied by the number of poles. The P, which we consider the number of poles, LF is the line frequency, which could be 50 hertz or 60 hertz. The first fault we have today is the stator eccentricity. And this is mean that the stator itself has some casing distortion and the rotor inside on the right direction, but the stator itself is twisted, have this distortion. The stator eccentricity or loose iron or shorted lamination can be seen on the motor and on the radial direction as the twice line frequency, 100 hertz or 120 hertz. As it produces uneven air gap, there will be uneven air gap variation or air gap variation between the rotor and the stator. And note the current peaks twice per cycle, once in the negative direction and once in the positive direction. And this causes two force pulsation per cycle, and that's what causes the twice line frequency. And soft foot can do the same thing. Like, if you have soft foot in your motor, it will do the same thing. And very good, you have some tricks to know this. The first one is called soft foot dynamic testing. Like, while the motor is running, you can lose one of the bolts of the motor, tighten again, go to the next one, tighten again, third one, tighten again, fourth one, tighten again. And while you're doing this action, you will have your sensor on the machine on the highest point, like, for example, in the horizontal drive end, this one showing the highest level of vibration. And if the vibration dropped when you lose one of these poles, and this means that you have soft foot, and because of the casing distortion, you see this twice line frequency, and also it can appear at the running speed. And also one other thing, you can, if you want to know if it's because soft foot or something electrical happened inside, you can turn this motor off while you collect the data. If you found that twice line frequency 100 hertz drop suddenly, definitely it's electrical problem. If it's gradually dropped, this is more mechanical problem. The second fault we have is the eccentric rotor. In the rotor eccentricity, you can see 1x, also twice line frequency, with sideband at the BBF, or the pole pass frequency, which is the slip frequency multiplied by the number of poles, and you will see it on the radial direction. Rotor bow and unbalanced rotor current will create uneven thermal growth on the rotor, which cause rotor to bow, and that create rotor imbalance, and it will be very similar to the unbalanced symptom. By the way, the thermal imbalance is one of the common things which could happen in the generator in a steam or gas turbine. The fourth one is the loss in the winding. It will create twice line frequency with harmonics. You will see the twice line frequency with many harmonics. And also when you have short in the stator, you might see the twice line frequency with harmonics. And you will see it on the radial direction, and it should be magnetic induced vibration at the twice line frequency with this harmonics. Also the crack or broken rotor bar. You will see the running speed with harmonics on the radial direction plus sideband and the ball pass frequency, which is the slip frequency multiplied by the number of balls. And in this condition, the motor current signature analysis is a very good way to detect this kind of faults. Some cases, you will not see 1x with harmonics plus the side bands at the ball pass frequency. You might see high amplitude at 1x only with side bands at the ball pass frequency, which is the slip frequency multiplied by the number of balls. You will not see the harmonics. You will see very high amplitude of 1x with this side bands, but with no harmonics. In some cases, you will see 1x with harmonics with side bands. The most common one is that one, 1x with harmonics. We talked about the broken or cracked rotor bar, but in this condition is the loose rotor bar, and this is you can distinguish between them this way. As we say, the cracked or broken rotor bar, you will see 1x with harmonics, sideband at the ball pass frequency, or very high 1x sidebands at the ball pass frequency, mostly in the low range. For the loose rotor bar, you will see the rotor bar passing frequency with sideband at the twice line frequency or the running speed, and this will be in the high range. Don't get confused. If you have very variable frequency drive motor, like for example, the line frequency, you know, it's 50 hertz or 60 hertz. So you can see that the rotor passing frequency have side bands, not at 100 hertz. It might side bands at 90 hertz or 89. Look for the frequency coming to the motor, the electrical frequency. Like for example, if you have 100 hertz as the twice line frequency, this means that your line frequency is 50 hertz. But if your line frequency is 40 hertz, like in variable frequency drive motors, so the twice line frequency at this condition will be 80 hertz. So you will see the rotor bar passing frequency with sideband at 80 hertz. So just be careful. Like don't say, it's not 100 hertz. You have always to be careful about what's the line frequency on the motor. The last one we have here is loss in the connection, and this is phasing problem due to loose connection on the junction box. Could cause high twice line frequency with sideband and 1/3 the line frequency. And as you normally have 3-phase, and in that case you will have like a phase imbalance. This is the most common faults for the electrical motors. I hope you liked the video. As always saying, I'm trying to make my videos short. If you have any comments, please leave it for me. If there's any improvements need to be done, please let me know. Please like, subscribe, and share, and thanks for watching.